Welcome to The Explainer. Today, we're diving into a huge concept in artificial intelligence, something that's quietly running in the background of your life, powering everything from your spam filter all the way to cutting-edge medical diagnostics. We're talking about supervised learning.
So let's just jump right in with a question that really gets to the core of it all. How on earth can a computer, a machine that just crunches numbers, learn how to predict the price of a house? I mean, it's not magic, right?
Well, the answer is actually pretty simple, and it's the big idea behind all of this. It's not about the computer being smart like a person. It's about its ability to see patterns in just tons and tons of data. We're talking square footage, number of bedrooms, location, and of course the final sale prices from thousands and thousands of other houses.
And this whole process has a name: supervised learning. Now, where does the supervision part come in? Well, you can think of it like this. We're the teacher. We give the machine a huge data set that already has all the right answers, or labels. We show it a house's features and its final sale price again and again until it starts to learn the relationship between the two.
So supervised learning is this really powerful tool, and it really shines at two basic jobs: predicting specific numbers and sorting things into groups or giving them names.
And this slide breaks those two jobs down perfectly. On one hand, when we're trying to predict a number that could be anything on a scale, like the exact price of a house, that's called regression. But on the other hand, when we're trying to predict a specific category, like a house's condition on a scale of 1 to 5, that's called classification. Bottom line, regression gives you a number, classification gives you a name.
All right, quick gut check. Let's say you're trying to figure out a penguin species. Is it an Adelie, a chinstrap, or a Gentoo, based on something like its flipper length? Is that regression or classification? Yep, it's a classic classification problem. You're sorting it into a specific, predefined bucket, not predicting some random number.
Okay, so we know what supervised learning does, but let's dig into the how. And we're going to start with a really simple, super intuitive algorithm that kind of gets to the heart of how this all works.
You know that old saying, right? Birds of a feather flock together? Well, that basically sums up the entire logic of an algorithm called k-nearest neighbors, or just KNN. The idea is so simple. If you want to know something about a new thing, just look at the things that are most similar to it and assume it's probably like them.
The algorithm itself is a pretty straightforward four-step deal. First, you decide how many neighbors you're going to ask. That's your K. Then, you calculate the distance from your new unknown item to every single other known item. Step 3, you find the K closest ones, and finally, you let them vote. Whatever the majority says, goes.
Now, to make this really concrete, let's look at a fun, real-world example from a research paper. A scientist used this exact method to classify different kinds of dry beans just based on their size and shape. Yeah, beans. It's a perfect way for us to see this in action.
So a computer has no idea what a bean is. It just sees numbers. In this case, it measures things like the bean's length, that's the major axis, and its width, the minor axis. And you can see here, different bean types like Horos and Syrah, they tend to have slightly different measurements.
All right, so here's the deal. We have a new mystery bean. We've measured it, but we have no idea what kind it is. So for our KNN algorithm, let's pick K equals 5. That just means we're going to find the 5 already identified beans that are mathematically closest to our mystery bean, and we're going to ask them for their opinion.
And here we go. The vote is in. The algorithm looked at the 5 closest neighbors to our mystery bean. It turns out 3 of them were the Horos variety and 2 were Syrah. So based on that 3-2 vote, the algorithm makes its decision. Our mystery bean is a Horos. See? It's like democracy, but for data points.
So classifying beans is kind of fun. But what's absolutely incredible is that this exact same logic, this idea of learning from your neighbors, can be used for problems that have insanely high, literally life or death stakes.
Because doctors, every single day, face this huge challenge. They have to look at cells from a patient's biopsy and figure out if they show signs of cancer. And obviously, the difference between a benign, non-cancerous growth and a malignant, cancerous one, well, it changes everything.
And just like with the beans, the computer doesn't see cells. It sees numbers. It gets fed measurable features from images of those cells. Things like their average size, their texture, how smooth they are. And it turns out benign and malignant cells have really different characteristics you can actually measure.
And these differences aren't just guesses. They're clear, quantifiable patterns in the data. Take a look at this chart. It's based on a famous medical data set,
and it shows that, on average, malignant cells have a much larger radius than benign cells. For a learning algorithm, that's a massive signal.
So using features just like that one, radius, texture, and so on, from thousands of samples that have already been diagnosed by doctors, the algorithm basically learns to draw a line in the sand. It's called a decision boundary, and it's the line that best separates the two groups. So when a new, unknown sample comes in, the model just checks to see which side of the line it falls on. And that's how it makes its prediction.
And that really brings us to the final amazing thought here. This stuff is not just about pricing houses or sorting beans. This is a tool that can amplify human intelligence in pretty much any field you can imagine. This ability to learn from examples is changing our world. And it really leaves us with one massive question. What important patterns should we teach our machines to look for next?